Hello guys, hope you all are doing well. So in the continuation of the previous GATE series, we are solving the questions of GATE 1991, and we are solving the section B. We have completed the section A. So today we have a new question of section B. So that is question 22, and the question is saying, actually the first question was theoretical, define what is work index. So I just skip that question. So we will start from the second question. So the second question, what the question is saying, the power required to crush 100 tons per hour of material is 179.8 kilowatt. Remember, kilo is a number, that is the value of 1000. If 80% of the feed passes through a 51 screen and 80% of the products passes through a 3.2 screen, what is the work index of the material? So solution, we know that if 80% of the feed passes through a screen of dp1 and 80% of the product are passing through of a screen dp2, okay, then we will apply Bond's law. So what is Bond's law? This is Bond's law, right? We all know power divided by the flow rate of the solids. 0.3162 is the bond constant, then into work index, then dp2 and dp1, right? Put all the values. So put all the values. So this is given, this is given. Okay, we have to find the work index. We have put the value of diameters, which is this is the feed diameter of the particle, this is the product diameter of the particle. So work index is coming 13.57 kilowatt hour per ton. Okay, now the second question in the continuation of that previous question, and that is a third part. What will be the power required for the same feed, that is 51 at 100 tons per hour? Flow rate is same. Okay, flow rate is same, 100 tons per hour. To be crushed, a product such that 80% of is to pass through 1.6 screen. Now they are just changing the screen size 1.6. Okay, they are changing the screen size 1.6. So apply again the Bond's law. Okay, so this is Bond's law. We just have found work index, so we'll put this value here, and we have to find the power. This is given, everything else is given. This is the initial 51 Okay, so we have put it the value. What we are getting the power, this. Okay, so this is a very uh, easy question, just based on the formula. The whole thing is there. Okay, now next question. So question 23 from heat transfer. What question is saying? In a co-current heat exchanger, an oil stream is cooled from 450 Kelvin to 410 Kelvin by water inlet and outlet temperature 300-350 respectively. The exchanger consists of a number of tubes of 1 meter length each. ये first case है. It is now desired to cool the oil to 390 instead of 410. We were cooling the oil at 410 in case first. Now in case second, we want to cool the oil at 390 Kelvin while maintaining the flow rate of oil, flow rate of water, inlet temperatures of oil and water, inlet temperatures of oil and water, not outlet temperature, because to cool the oil from 410 to 390, a long tube is required. That's why the temperature of the outlet will change. Okay, so the number of tubes as the same as before, n. Okay, in case 1 we will assume n tubes, In case 2 we will assume n tubes, so that is same. Calculate the length of each tube required for this purpose. Okay, so very first thing, in the case first, in case first, inlet oil temperature, that is hot fluid 450 Kelvin, and is going through the tube, through the shell 410 Kelvin, and water inlet 300 Kelvin and outlet 350 Kelvin. Who the operation is co-current, right? Case 2, instead of 410, we want to cool the oil at 390 Kelvin. That's why this is the case first of 350 Kelvin. This temperature at 390, temperature corresponding to 390 of cold fluid will change. Okay, so applying energy balance in a heat exchanger. Heat lost by the hot fluid is equal to heat gained by the cold fluid. So mCp delta T hot equal to mCp delta T of cold, mHCp TH1 minus TH2. This is TH1, this is TH2, this is TC1, this is TC2. Okay, so putting all the values. Okay, so since mass flow rate is not given, Cp of oil is not given, Cp of water is, we know that, but we will not put the values, hence mass flow rate of the water is not given. So the ratio, this ratio will come 50 by 40. We will mark it as 1, right? Now in case 2, apply energy balance. This is the final equation. Okay, since mass flow rate is not changing, specific heat will not change, physical property remains same, physical properties remain unchanged, right? So Cp will not change. So just simple mathematical things and calculating 3C2 for case 2, because on, if we want to cool the oil at 390, then corresponding temperature will change. So the TC2 will come 375 Kelvin. Okay, now, so this is the diagram. Case 1, we know that mCp del T of hot fluid, mCp del T of cold fluid is equal to UA theta m. Overall heat transfer coefficient, area of the cross sectional of the heat transfer, and theta m is the log mean temperature difference. You can take any of the value, either this equal to this or this equal to this equal to this. So I am taking hot fluid is equal to UA theta m, putting all the values. mHCpH TH1 minus TH2 is equal to U, n is the number of tube, pi dl is the area of tube, so n into area, so that is the total number of the tube, total area of the tube into theta m1, right? In case 2, similar, I am taking hot fluid and this mHCpH TH1 minus TH2 U n pi d L2 here comes, because length will change, we have to find the new length theta m2, right? Dividing equation 2 and 3, 2 and 3 go divide kar, which is 2 is this and 3 is this. Okay, so mHCpH will remain same, it will cut out. Okay, TH1 minus TH2 in the case first is different, TH1 minus TH2 in the case 2 is different, right? U will cut because physical conditions say, n number of tube is same, pi is the constant. Okay, diameter is not changing. Okay, so what else is remaining? This. For case 1, 450 minus 410, 450 minus 410, right? 450 minus 410. And for case 2, 450 minus 300, 450 minus 390, sorry, 390. 1 is the length for case 1 of the tube. So 1 into theta m1 divided by L2, we have to find theta m2. What is theta m1 and theta m2? So theta m1 is, for case 1, 450, this is theta 1, Okay, this is theta 1 for case 1, and this is theta 2. Okay, sorry, this is theta, this is theta 1, this is theta 2 for case 1. This is theta 1 and this is theta 2 for case 2. Okay, so 450 minus 300, 410 minus 350 divided by this, and 450 minus 300 minus 390 divided minus 350 divided by this. Okay, so we'll get theta m1 will be 98.2 and theta m2 will be 58.6. Okay, so finally, after calculating length of each tube after for cooling, the temperature at 390 instead of 410 will come 2.51 meter. Okay, so hope you will understand this question, and if you have any doubt, just comment it below. Okay, next question. A horizontal steam pipe, a horizontal steam pipe 20-meter long, 50 mm internal diameter and 60 mm outside diameter loses 30.5 kilowatt heat to the surroundings at 310 Kelvin. The pipe carries steam at 500 Kelvin and the convective heat transfer coefficient is given by this. Stephen Boltzmann constant, we all know that the value. Find the emissivity of the bare surface of the rod. Okay. So very first thing, understand the question. Where is the cursor? Okay, yeah, right here. Okay. So we have a steam inside the pipe that is at 500 Kelvin and surrounding is at 300 Kelvin. 13.5 kilowatt heat loses to the surrounding. 60 mm is the outside diameter and 50 mm is the internal diameter. Okay, and 20-meter long the pipe is. Now we have to calculate the emissivity of the bare rod of the pipe. Okay, so Q is equal to will be the summation of heat transfer through convection and heat transfer through radiation. Okay, now just put everything. 1.65 H is 1.65, del T 0.25, area is the outer surface area we will consider because ultimately the heat transfer is going through the outer surface area. Okay, so we'll consider the outer surface area. Then del T, similarly for radiation, this is radiation and this is for convection. This is for, this whole term is for heat transfer due to convection and this whole term is due to heat transfer due to radiation, and it is summation of the, because heat will go out as a combination of heat transfer through convection and heat transfer through radiation. So 1.65. Okay, and putting all the values, sigma E A naught del T ki power 4. This del T ki power 4 actually is T1 to the power 4 minus T to the power 4. Okay, so I just write it in short form. It is not, you will it is not like that. T1 minus T2 the power 4. Okay, it is not like that. It is wrong. It is right. This is right. Right. So we'll see later. So one del T is here. One del T is this one. Another del T is 0.25. So it will result in 1.25 A naught sigma. Now putting all the values, 1.65 del T, 1.25 A naught, 5.67 into 10 to the power minus 8 sigma A naught del T to the power 4, 1.65 del T into area is pi d naught L, 5.67 10 to the power minus 8 sigma pi d naught L del T to the power 4. Now Q is 13.5 kilowatt, 1.65, 500 minus 310 1.25 into pi d naught L plus 5.67 into 10 to the power minus 8 pi d naught L into 500 की power 4 minus 310 की power 4. So this is the thing I am talking about here. Okay. Now solving further, 13.5 kilowatt, 1.65, 500 minus 310, 1.25, pi dl, pi d naught L, 5.67. Now this 10 to the power 8, where it disappear? It does disappear. Sigma pi d naught L is the same as it is here, right? But this 10 to the power, what I did, I just divided, I just divided this 10 to the power minus 8 here. I put this inside this bracket, and since it is 10 to the power 8, so you will result in 5 to the power 4 minus 3.1 to the power 4. That will make the calculation easier, or you can calculate it like this as well. Okay, like this as well. Okay, so what will be the answer? This is the area. So our answer is emissivity of the bare rod will come 0.80. Okay, so this is the same. So hope you understand all the three questions. Okay, so if you have any doubt, then just comment it below. Okay, I'll try to reply as soon as possible. And we have remaining with few questions. I will upload it uh, as soon as possible. And stay focused, guys. Keep practicing. The exam is very near. Okay, bye guys.